Well, hello there. This is Ron. Welcome to Mom. This is a second video for bending stress video 2. So I've got a little beam here. It's 4 meters long, and on the right 2 meters there's a 3 kilonewton per meter distributed load. What I would like to do is to find the maximum stress in this beam. I'm going to tell you a little bit more about the beam. The beam is a T-beam, and in the T-beam every dimension is 10 centimeters. 10 centimeters, 10 centimeters. That's I don't mean every dimension. And then this dimension is 40 centimeters, and this dimension is 30 centimeters. So the widths are all 10 centimeters. So 10, 10, 30, 40. And I want to find the maximum bending stress in this beam. Well, as we already know, this is kind of a two-part problem. And the first part is to find where is the maximum moment in the beam. In other words, what location has the maximum moment. And the equation for bending stress, as we know, is my over I. So we'll use the beam to get the m. And then we're going to have to spend some time on this cross-section to find the centroid, to find the I, and to find the Y. But let's do part 1 to begin with. If you do the reactions, 3 kilonewtons per meter times 2 meters, that will give us 6 kilonewtons. And if you sum the forces in the Y and sum the moments, you will get that 4.5 kilonewtons act up here, and 1.5 kilonewtons act up there. If you want the practice, I would suggest that you press pause and sum the forces in the Y and sum the moments about any point to do that math. It would be a good thing to do. Alright, so now we're going to quickly do the shear and moment diagrams. And I would recommend, again, that you press pause, draw the shear diagram. And now I'm doing it 1.5 meters, or 1.5 kilonewtons rather. Nothing. Now I need to go down 6 kilonewtons. And if I'm at 1.5 and I go down 6, I get to negative 4.5. I don't have this drawn to great scale. Now we need to calculate the areas. And this takes a little bit of geometry for us to calculate the areas. Well, first of all, 1.5 kilonewtons times 2 meters is, here's an area of 3. This height is 1.5. Here's the problem. We don't know that distance. But we're going to get it using similar triangles. We know that for this big triangle here, we have a height of 6 and a base of 2. And for this little triangle, we have a height of 1.5 and a base of, I'm just going to call it x. And from similar triangles, what you do is you take a ratio of the like sides. So x is to 1.5, x is to 1.5, as 2 is to 6, as 2 is to 6. And that allows us to multiply both sides by 1.5. 2 times 1.5 is 3. 3 over 6 is a half. So x equals a half a meter. And that means this will be 1.5 meters. So I didn't do a great job of drawing this to scale, but we have our distances here. 1/2 base times height, we have a half times a half is a quarter times 1.5. I better grab that off my phone so I don't screw it up. So getting the area of this triangle, 1/2 base times height, I get 0.375. And over here, my 1/2 base times height is going to be 1/2 of 1.5 times negative 4.5. And I get a negative 3.375. All right, there we go. Where this crossed the x-axis is a new important point. So here we go. I'm now going to draw the moment diagram. Again, it would be worth pressing pause. Okay, so I start at 0. As I go from here to here, I'm supposed to go up 3. Horizontal line, inclined line. As I go from here to there, the next two important points, I need to go up by 0.375. So I was at 3. Now I'm going to be at 3.375. This is an inclined line, so this is going to be a parabola. The value of shear there is 0, so the slope needs to be 0. So that's kind of curved there. As I go to the next important point, I need to go down, because that's negative 3.375. I start at 3.375, I go down to 0. And again, v is 0, so the slope is 0. And there's our moment diagram. All right, making some progress. So now, if the sigma is equal to my over I, and I now know where's the maximum moment, well, it is right here at a distance of 2.5 meters from the left end, or 1.5 meters from the right end. Okay, so that's m. M is 3.375 kilonewton meters. Now we need to spend some time on this shape. So the first thing I need to do is I need to find the centroid. So real quick, I'm going to now go into meters, 0.1 meters, 0.1 meters, 0.3 meters, 0.4 meters, and I will calculate the centroid I'm looking for is the up and down centroid, so that's the y bar. So I'm going to come from right here and I'm going to find how far is it that way to y bar. I'm going to break this into two pieces. We'll call this piece 1 and this piece 2. And y bar equals the sum of y bar A over the sum of the areas. Well, for piece 1, it's y bar. Its distance from here is 0.3 and half of that, so 0.35. So 0.35, and its area is 0.1 times 0.4. Y bar A for piece 1. Now, plus, sum, plus, y bar A, so piece 2 is going to have a y bar of 0.15, half of that, and an A of 0.1 times 0.3. Divided by, let's do this math, 0.1 of 0.4 is 0.04, 0.03, add those together, 0.04 plus 0.03. All right, so I wish you would run that through your calculator. I'm going to press pause and do the same. So when I did that, I got 0.2642, and I think for the sake of good math here, I'm just going to round to 0.26. Well, that means that the centroid of this composite piece is 0.26 meters from the bottom. That means that to the top fiber, if this is 0.3 and this is 0.1, the whole distance is 0.4, 0.26, and 0.14. So this would be the neutral axis. The y's for to the top fiber is 0.14 and to the bottom fiber is 0.26. So the max y is going to be the 0.26. So there's our y. Now we need to find I. So we need to find I for this whole piece about its own centroid. And here's the parallel axis theorem. I for the whole piece is I for piece 1 about its centroid plus area 1 d1 squared plus I for piece 2 about its centroid plus area 2 d2 squared. Well, let me run through those real quick. I bar 1 is 1/12 of bh cubed. B is 0.4. H is 0.1. The area for piece 1, we already know, is 0.04. And the distance is the distance from the centroid of piece 1 to the neutral axis. That's the D in the parallel axis theorem. Let's see, it's 0.26, so it's 0.04 up to the bottom, and then another 0.05, it's 0.09 squared. So D1 is 0.09. That's this distance right here, 0.09. The distance to the centroid of piece 1 from the neutral axis. So there's I1, A1, D1 squared. I2, 1/12 BH cubed plus A2 D2 squared. Now piece 1, or piece 2 rather, its centroid is half of 0.13, so 0.15. And 0.26 is the neutral axis. So from 0.15 to 0.26, that's this distance right here, is 0.11. So I1 is 1/12 times BH cubed plus AD squared, 1/12 BH cubed plus AD squared. All right, I think you should do the math. I will do the same. Oops. This is I bar for the whole works here. Well, I1, A1 D1 squared, I2 A2 D2 squared. Get rid of that subscript. So that's the thing we're looking for. That's what we're going to put in the bending stress equation once we do the math. You do it, I'll do it, meet back in the middle. All right, well I did this in Excel, put all that in, and of course we're all prone to calculator errors, but when I did, I got 0.000945 meters to the fourth. So, the maximum bending stress will be where the moment is the max, and that is at this point. And the maximum moment is 3.375 kilonewton meters. times where y is the max, and the maximum y we got was 0.26 meters from the neutral axis to the furthest point, divided by I for the whole cross section, which is 0.000945 meters to the fourth. Now we have meters and meters squared. So we're going to have an answer in kilonewtons per meter squared, which is also known as a kilopascal. And we put that into the calculator. I'll keep us live here. I'm doing this off on the side of my calculator, equals 3.375 times 0.26 divided by 0.000945. I get 928 kilonewtons per meter squared. 928.6 kilonewtons per meter squared. All right. And if we bend this the way that it's drawn there, the middle will come down, and the top fibers will be put in compression, and the bottom fibers will be put in tension. So this would be 928.6 kilonewton per meter squared in tension. Please write down any questions you have to ask me in class. Have a nice day.